we're going to consider a special type of probability distribution. It's called the binomial distribution. Now recall that a probability distribution looks at the different values of the random variable and looks at every single one of those values and its corresponding probability. There are three common types of probability distributions that we run into. So we have one that's here, and we call this a right skewed distribution, because as you notice, the tail, I guess the tail kind of goes out to the right. If you imagine this to be the tail end, almost like a Godzilla-like figure, the tail is kind of out on this end. We sometimes also say simply that it's skewed to the right. This one, on the other hand, has the tail out to the left, so we call it a left skewed distribution. And this one is supposed to look kind of symmetric, so if you kind of were to superimpose a curve over it, you kind of get something that looks a little something like this. Now this one kind of almost looks like a bell shape. And so because it's, if you were to take a line and draw it down the center, you'd have two roughly perfectly even pieces on the left and right hand side. And so since you have the symmetry, we call it a symmetric distribution. Well, they obviously tell us different things. This one tells us that for the smaller values of x, we have higher probabilities, and for the bigger values, we have lower probabilities. This one tells us that as the values of x increase, the probability increases. And this one tells us that there's a point where the probabilities are highest, and then the tails to the left and the tails to the right are less and less probabilistic. So these are the most common types of distributions. Let's endeavor into an example now that uses this particular type of distribution that we're going to consider, which is a binomial. So suppose we have this company, Brighter Now, and they manufacture LED light bulbs and sell them in 4-packs. Unfortunately, the company has had some fairly high defect rates. It finds that 20% of its light bulbs are defective, independently of any other light bulbs that are manufactured with it. So the likelihood of one does not affect the likelihood of the other. The company would like to know the probability distribution for x equals the number of defective light bulbs in a 4-pack along with the expected value for x. Okay, so this might be a point to kind of pause the video and think about what it is that we're looking at here. And what we're considering, I'm going to draw it right below. This is sort of the first light bulb in the pack. And the first light bulb can take on one of two values. So it can be either defective or it's not defective. And the reason I'm using D and N is because if we use the bar over the top of the D, this table can really get hard to follow, and it already is. So I'm using D and N just to keep it clear. Well, if the first light bulb is defective, the second one is either defective or not defective, and so that's the second light bulb. And then this branch is the third light bulb, and this branch is the fourth light bulb. So you notice that there are two possibilities at each stage. 2 times 2 times 2 times 2 tells us there are going to be a total of 16 possibilities. And the way I like to write these out, and I know this one's kind of cut off, this is D, 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 D. And the way I like to follow these is to look at each of these leaves, as I call them, because they're on the outside of the tree diagram, and see how do I get there. So this would be D, 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 and that gives me 4 Ds. D, D, to get to this one, I'd have to go D, 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 N. To get to the next one, I'd have to go D, D, N, D, and so on and so forth. So I've listed out all the possibilities. Now, X in this situation is keeping track of the number of defective light bulbs. So most importantly, what values can X take on? Well, in a 4-pack, there could be 0, 1, 2, 3, or 4 defective light bulbs. So I'm going to write down little x and say the values are 0, 1, 2, 3, and 4. And the probability of getting that x value, well, that's what we've got to figure out. Now, we can't just say each of these is a 1/16th likelihood, because the probability of going this route is much less likely than the probability of getting 4 non-defectives, or at least maybe not that much more or less likely, but the likelihoods are different. They're not 50% defect, 50% non-defective. So we have to use a little bit of the AND rule here. So if I get 0 defective, that means I have all non-defective. So I'm going to change my color here so that we can follow along.